This is the graphing calculator open response question. We've got half an hour to do it. First question, we've got a table. Grain is being added to a silo. At time t equals 0, the silo is empty. The rate at which grain is being added is modeled by the differentiable function g, where g of t is measured in cubic feet per minute between 0 and 8. Selected values of g are given in the table above. Using the data in the table, approximate g prime of 3, and then using correct units, interpret the meaning of it in the context of the problem. Well, g prime of 3 is going to be approximately equal to the average rate of change of g over an interval containing 3. So the smallest interval containing 3 is the interval 1 to 5. So I'm going to compute the average rate of change over that interval. That would be g of 5 minus g of 1 divided by 5 minus 1. From the table, we can see that that's 20.5 minus 15.1. And so that's, whatever it is. You can use your calculator to evaluate it, or not, because you don't have to simplify your answers. But it looks like it's 1.35, right? So 1.35. What are the units? Well, g itself is already a rate measured in cubic feet per minute. And what we're looking at is the rate of change of g. So the units are going to be the units of g itself divided by the units of time, which is minutes. As I said, the units of g itself are already measured in cubic feet per minute, and then dividing by time again, it's cubic feet per minute per minute. If you like, you could simplify this as cubic feet per minute squared. So that would be the units, cubic feet per minute squared. Now, what is the meaning of this? Well, this is the rate of change of the rate at which grain is being added at time 3, which of course means 3 minutes. So I think that's the interpretation. 1b. Write an integral expression that represents the total amount of grain added to the silo from time t equals 0 to time t equals 8. Then use a right-Riemann sum with the 4 subintervals indicated by the data in the table to approximate the integral. Right, so g is the rate at which grain is being added. So if you integrate, it's kind of like a rate-in function. If you integrate this guy from 0 to 8, that would give you the amount of grain which is added. So we could say amount added equals this guy right here, is what I would write. And then to use a right-Riemann sum to approximate this integral, so the intervals are 0 to 1, 1 to 5, 5 to 6, 6 to 8. So the first rectangle sitting above the interval 0 to 1, its width is 1, and its height is 15.1, right? Because we're using the right endpoint. Plus, the next subinterval is 4 wide. And how tall is it? It's 20.5. The next subinterval is 1 unit wide. And it is 18.3 units tall. And then the last subinterval is 2 units wide, and it's 22.7 units tall. You can use your calculator to evaluate that, or you can just leave it. And so that is the approximation. So that's what I would say. Okay, so part C. The grain in the silo is spoiling at a rate modeled by W of t equals blah, 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 where WT is measured in cubic feet per minute. Using the result from part B, approximate the amount of unspoiled grain remaining in the silo at time t equals 8. So this is the rate at which grain is being spoiled. That means that at time t equals 8, the amount of unspoiled grain is going to be the following. It's the initial amount of grain that we started with, because I do believe that you start with some grain before the process even begins. Oh, no, I'm wrong about that. The silo is empty at t equals 0. So there is no initial grain to consider. So it's the amount of grain which is added to the silo over the course of the first 8 minutes, which a moment ago we found is this number right here. Let me actually compute what that is. That's 15.1 plus 4 times 20.5 plus 18.3 plus 2 times 22.7. 160.8. So it's 160.8 minus the amount of grain which spoiled over those 8 minutes, which would be the integral from 0 to 8 of this W of t. So I have to compute this integral. Of course, this is a calculator section, so I can just use my calculator. So W of t is equal to 32 square root sine pi t over 74. And I want to integrate from 0 to 8 W of t dt, 99.0514, blah, blah, blah. So 168.8 minus that number would be 61.748 approximately. Actually, remember you want to round, or you don't have to round, you can just leave more decimal places. 748. If you did round to the third decimal place, I think it would be 0.749, right, if you were to round it. So that would be my answer for C. Part D, based on the model in part C, is the amount of unspoiled grain in the silo increasing or decreasing at time t equals 6? So we know that at t equals 6, we actually know what the rate in function is. Like, we know the exact rate at which grain is being added to the silo at time t equals 6. It's 18.3. So I think what you want to consider is the difference, 18.3 minus, so that's the rate at which grain is being added at time 6, minus W of 6. That's the rate at which the grain is spoiling. And so I think that if this figure is negative, then the rate at which grain is spoiling is greater than the rate at which new grain is being added. So overall, like, the amount of spoiled grain would be increasing. So what is W of 6? That's 16.06. So this figure, 18.3, minus W of 6 is 2.237 approximately, which is positive, which is telling me that at this moment, grain is being added at a rate faster than grain is spoiling. That tells me that the amount of unspoiled grain is actually overall increasing. Cool. So that is number 1. Number 2, a snail is traveling along a straight path. The snail's velocity can be modeled by blah, inches per minute for t between 0 and 15. Find the acceleration of the snail at time t equals 5 minutes. I would not bother taking the derivative of this function manually. This is a calculator question. You can just ask your calculator. So v of t is 1.4 natural log of 1 plus t squared. And the acceleration at t equals 5, this is 2a. The acceleration at t equals 5 would just be v prime of 5. So that's o point. So v prime of 5 is 0.538461. So that's the acceleration, and the units which we should include are inches per minute squared. Okay. 2b, what is the displacement of the snail over the interval 0 to 15? Displacement is just the integral of the velocity function. So from 0 to 15, v of t dt. It's not the absolute value. Distance traveled would be the integral of the absolute value. This is displacement, so it's just regular v. So integral from 0 to 15, v of t dt, 76.043. Cool. Oh, and the units, what are the units? Inches. 2c. At what time t between 0 and 15, is the snail's instantaneous velocity equal to its average velocity over the interval 0 to 15? A little bit like a mean value theorem kind of question. So the average velocity over the interval 0 to 15 would be what? Well, you might be thinking to yourself, oh, I need to find the position function and then compute the average rate of change of that position function over 0 to 15. That would work, but you're not going to find the position function. This guy's too complicated. You're not going to find an antiderivative. You don't need to. There's an alternative way. The average velocity over 0 to 15 can also be found by simply computing the average value of the velocity function. So that's 1 over 15 minus 0 times the integral from 0 to 15 v of t dt. So what is that quantity? Well, it's just 1/15 of the number we just found previously. So that's 5.069538, blah, blah, blah. So that's the average velocity. When is the instantaneous velocity equal to that number? The instantaneous velocity is just v. So we're asking, when is v of t equal to 5.069538, blah, 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 right? That's our question. To answer that, you can say, on your calculator, v of t is the function 1.4 natural log, blah, blah, blah. So this is the equation 1.4 natural log 1 plus t squared equals 5.069538. You can solve this equation on your calculator by just subtracting that number from both sides. And then graphing this function in your calculator and seeing when is it equal to 0, like where are its x-intercepts. So if I do this guy minus 5.069538, Here it is. Where is it equal to 0? Right here. Looks like right there. 6.031. So 6.031, that's measured in minutes. So that is the moment at which the average velocity matches the instantaneous velocity. Okay, and then finally D. I vaguely remember doing this problem many years ago and thinking that it was like very difficult. I don't really remember what it's about though. Yeah, so I have some recollection about this problem being very difficult, but I don't really remember. D, an ant arrives at the snail's starting position at time t equals 12 minutes and follows the snail's path. Okay. During the interval 12 to 15, the ant travels in the same direction as the snail with a constant acceleration of 2 inches per minute per minute. So I'm going to call the acceleration of the ant a of t, and it's just a constant 2. The ant catches up to the snail at time t equals 15 minutes. Okay. The ant's velocity at time t equals 12 is b inches per minute. Find the value of b. Yeah, this is hard. Off the top of my head, I don't know how to do it, so I have to think. So I know that because the acceleration is constant, the velocity function will be 2t plus some unknown c. Now, I know that the ant's position, or what I can say is that the ant's position has to be the same at t equals 15 as the snail's position at t equals 15. So the ant's position at t equals 15 would be its starting position, which is the same as the snail's position, plus the integral of its velocity function. Okay. So I'm going to write integral from 12 to 15 of 2t plus c dt. And that needs to be equal to, that's how far the ant goes over this time interval. And that distance needs to be the same as that displacement, I should say, needs to be the same as the displacement as the snail's displacement, right? Over the entire 15-minute interval, which we have here, the 76.043. I'm a little worried. I kind of want to get that value a little bit more precisely. So integral from 0 to 15, what's the velocity function? It's 1.4 natural log 1 plus t squared dt. Yeah, so 7.043073. Okay, that should be enough. So basically the ant's displacement needs to be the same as the snail's displacement, right? The ant's displacement over the minutes from 12 to 15 should be the same as the displacement of the snail over the course of the entire 15 minutes. So this integral needs to come out to be 76.04307338. Now, what is this integral? The antiderivative would be t squared plus ct evaluated from 12 to 15. And that needs to be equal to 76.04307338. So 15 squared plus c times 15 minus 12 squared plus c times 12 that needs to be equal to 76.04307338. So, what's up?
Did you give out like another packet yesterday or no?
Yeah.
Awesome.
No, it's not that one. Hold on.
No, okay. And the I saw on Canvas like the AP practice.
Yeah.
That's just like an extra.
Mm-hmm.
Right?
Yep.
Alright, cool.
Later. So anyway, so 15 squared is 225. So this is 225 plus 15c minus this is 144 plus 12c equals this same number. So 225 minus 144 is 81. And then 15c minus 12c is 3c. So I get 3. So c is going to be 76.04307338 minus 81, all divided by 3, which is negative 1.6523. Which means that the velocity function for the ant, I shouldn't have called this v of t because v of t already means the velocity function of the snail, but too late now, whatever. Maybe I should call it v sub ant, right? Give the subscript there just to distinguish it. So that's 2t minus 1.6523. So now that I have the velocity function of the ant, I know that the ant's velocity at time t equals 12 is b inches per minute, find the value of b. So they're just saying find the ant's velocity at time t equals 12, which I can do easily now by plugging in 12 for t. So 22.3477. What was that again? Is that right? 22 point. Of course, this is inches per minute, right? Let me check that. Yeah. There it is. Cool.